So something pretty remarkable just hit the wire in the last few hours. Out of Tunisia, two papers have appeared online, not from a big research institution, but from a single independent researcher named Saif Allah Maflouthi. And look, the claim they're making is staggering. They suggest that the solutions to two of our field's absolute biggest challenges, P versus NP and the path to AGI, aren't actually mathematical or computational problems at all. They're philosophical ones. It is a profoundly bold thesis. So let's really dive in and unpack this argument. And this question right here, this is the absolute heart of the entire argument. The idea is that maybe the roadblocks we keep slamming into in complexity theory and in AI, maybe they aren't about needing a more clever algorithm or just, a bigger data set. Maybe it's about being brave enough to admit we might have a fundamental error in how we're framing the questions in the first place. All right, so here's how we're going to break this down. First, we'll quickly touch on the grand challenges themselves. Then, we'll dig into this idea of two domains to reframe P versus NP. From there, we'll pivot to AI and its current limits, look at a really novel solution that's rooted in language, and finally, we'll tie it all together with this concept of the philosophical engineer. Okay, Section 1, Computation's Grand Challenges. Now, you and I, we all know these problems inside and out, but it's really worth taking a moment to just revisit the conventional way we think about them, because that's precisely the foundation these papers are trying to dismantle. So you've got the two big ones. On one hand, P versus NP, the classic question that's been haunting us for decades. Does being able to quickly check an answer mean you can also quickly find it? And on the other hand, the white whale, AGI. How do we get from the brilliant but brittle pattern matching of today's language models to something that has genuine semantic understanding? These are the two mountains Maflouthi is claiming to have a totally new map for. So let's get into that first paper's take on P versus NP. And here's the first big twist. This isn't about some new, complex mathematical proof. Not at all. Instead, it's about stepping way back and deconstructing the very terms we use to define the problem itself. The central claim here is that this 50-year stalemate we've been in exists for one simple reason. We're unconsciously mixing up two totally different ideas. The argument is that the problem isn't a lack of mathematical genius, but what the author calls an epistemic ambiguity in our very definition of computational time. And this visualizes that core distinction perfectly. On the left, you've got the formal domain. This is our perfect abstract world of Turing machines where time is just a symbolic counter, totally unbounded by physics. But then, on the right, you have the physical domain, the real world where computation actually has to happen and where time is ruthlessly constrained by causality and entropy. The paper's insight, and it's a profound one, is that our gut intuition that P does not equal NP is a physical intuition. Yet we've been trying to prove it exclusively in the abstract formal domain. And this leads to the paper's central concept. P versus NP isn't a problem that lives neatly inside one of these boxes. It's what the author defines as a boundary phenomenon. The difficulty, the hardness of the problem actually comes from the structural tension between these two domains. We've been trying to solve a problem that exists in the gap between two different conceptual universes. Now let's pivot to the second paper, which takes a very similar deconstructive lens and applies it to AGI. It kicks off by trying to diagnose why our most advanced models, even the ones that feel so powerful, still seem so fragile and, well, fundamentally unintelligent at times.
And the paper argues that AI hallucinations aren't some minor bug we can just patch with more data. They are a massive red flag, a symptom of a deep architectural flaw. Our models today are incredible statistical engines, but they have absolutely no internal, self-correcting structure for actually validating the meaning of what they produce.
The author diagnoses this as a tripartite dissociation of meaning. Now, it's a bit of a mouthful, but the idea is actually very simple and powerful. You have the symbol, the word itself, you have the conceived meaning, the internal concept, and you have the referent, the actual object out there in the world. A hallucination is what happens when those three things become unmoored from each other. The system can string together symbols that look right, but they're semantically empty because there's no mechanism to keep those three layers coherent. Okay, so if that's the diagnosis, what's the prescription? This is where the argument takes a really fascinating turn, proposing a blueprint for AGI from a source that many of us probably haven't considered: The proposed solution is to look to linguistics, specifically to the underlying structure of the Arabic language. Now, let's be crystal clear about this, because it's a crucial point. The author is not saying we should teach AIs to speak Arabic. The proposal is to use its incredibly regular root-based generative morphology as a computational model, a blueprint for building systems that can actually validate their own semantic outputs. And this slide maps that idea out beautifully. Think of a three-consonant root in Arabic, like KTB, which relates to the concept of writing. That functions like an abstract class in software engineering. The morphological patterns you apply to it, those are like generative functions. And the resulting words that pop out, kitab for book, maktab for office, are instantiated semantic objects, each with predictable, logically linked properties. It's a system with built-in semantic coherence from the ground up. So how do these two threads, a reframing of complexity theory and a new blueprint for AI, actually connect? Well, the synthesis, the real connection, lies in the underlying method that's being used for both. The common thread is this method of what's effectively being called philosophical engineering. In both cases, the breakthrough doesn't come from a new algorithm or a new equation. It comes from first identifying a hidden, unexamined philosophical assumption about the nature of time in P versus NP, and about the structure of meaning in AGI, and then engineering a new conceptual framework that actually deals with it head-on. And this quote from the author really just crystallizes the whole point. The objective is not to construct an intelligence that speaks Arabic, but to develop intelligent systems that operate according to a linguistic logic. See, it's not about cultural specifics. It's about finding a robust, working model out there in the wild, in this case, a natural language, that already exhibits the properties you want, and then abstracting its logic into a formal computational framework. So the ultimate takeaway is this. Two of our field's most formidable, long-standing challenges and a single proposed key. The argument is that the path forward is unlocked not by better math or more compute, but by a better philosophy, a fundamental reframing that finally allows the technical solution to become visible. And so, it leaves all of us with a really provocative question to take back to our own work. What are the foundational, unexamined assumptions that are embedded in the problems that you're trying to solve right now? And could it be that our next great breakthrough is hiding in plain sight, disguised not as a technical puzzle, but as a philosophical blind spot?